Lecture here. So as I sent out, in the announcement, we are going to actually start with chapter 4 today. Those that had discussion on Monday, we talked about sort of the rest of chapter 3 for the most part. Those that have discussion today on Wednesday, we will also lecture a little bit in chapter 3. And the part that we didn't get to in chapter 3 for both sections of the class. What I think I'm going to do on that is I will post a kind of recorded video for that last little section of chapter 3. So again, those that had discussion on Monday, we actually continued lecturing on chapter 3. We got almost done with all of it. And again, those that do have discussion today, we will continue lecturing on chapter 3. Just to wrap it up. Again, just so we could kind of keep on pace here, we had a couple of things occur. Obviously, the holiday, we also took quiz, just took out some time from lecturing and stuff like that. So just to try to keep us kind of on pace and not get too far behind, that's sort of the game plan here. So again, we're going to go rolling into chapter 4 at this point. We will definitely, again, for those that have discussion today, go back to chapter 3 and discuss some of that, just like we did on Monday for those people that had discussion on Monday. And like I said, there is one part, I think, of chapter 3 we won't get to for in both parts. And I will record a sort of probably video on that and post it. So everybody will be on the same page in terms of that. Again, these notes should be up there, obviously, on our Canvas site. And other than that, I think we'll get going here. So in this chapter, we're going to talk about a number of things. There's a lot of sort of information in this particular chapter. Excuse me. As the sort of title implies there, we're going to talk about the atom, talk a little bit about some experiments and discovery in terms of the atom, what led to sort of our understanding of the nature of the atom. We'll also talk about the periodic table. We'll also talk about elements and symbols in this chapter. We will talk about as well, basically electron configuration and everything kind of towards the end of this chapter. And then we'll talk finally, I think, in terms of periodic trends and stuff like that as well. So a lot rolled up into this chapter. So let us get going on it. So atoms and elements. So we talked a little bit about the idea that really, atoms are the basic sort of unit of every element. So, elements are, as we talked about, sort of as far back as you could go in terms of, making stuff or making matter or substances, I guess, in that sense. As we talked about, there's only so many elements. But different combinations of those elements will obviously result in different compounds that are made. But what really represents elements are atoms. Atoms are obviously much smaller, as we'll talk about here in this chapter, basically made up of smaller particles like protons, electrons, and neutrons. So when we talk about elements, there are elements are represented. You can see them on the periodic table. So if you have a periodic table in front of you or near you, you see obviously all the different elements. They are represented by symbols. So we do represent elements through symbols. And as you look at the periodic table, or maybe you've looked at it before, and as we'll talk about, really symbols are either one letter or sort of two-letter symbols like what we see here. In terms of aluminum, which is Al. As we'll talk about, basically the first letter is capitalized, the second one is not. They could also be one letter sort of symbols, like C is for carbon. We also have H for hydrogen as sort of the symbol. A reminder as well that, some elements, as we talked about, do come as diatomic molecules. So there are certain elements that how they naturally come, like hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, and iodine. Again, this is naturally how they just come about by themselves, is as twos basically, which are these diatomic molecules. But again, if you're asked to write the symbol for hydrogen in a formula, it is just H. But if it's just hydrogen gas by itself, it would be H2. Again, that would be the correct chemical formula for hydrogen. This would be the correct symbol for something like hydrogen. So there's that little distinct difference between those two things. But when we're really talking about elements, symbol here, we're talking about like really what you see on the periodic table. Elements, as we talked about, is pretty much as far back as you could go. So, you can break up compounds back to elements. So if you have compounds, which again, as we talked about, is really a combination of two or more elements together, you could break those up by some type of chemical process into elements. But again, as far back as you could go is elements. You can't really break that back into anything sort of smaller than that. Elements in their names, they really do come from a wide variety of sources, the sort of names and really sort of the symbols that we associate with it. And that's why, for example, we look at something like iron, right? And iron is like spelled like that. But yet the symbol for iron is Fe, and it's really based on sort of the origin of the name. Also, like lead, for example, lead is this, and the symbol is Pb. Again, really based on sort of the origin of the name. Sometimes they come from, as it says here, planets, mythological figures, minerals, locations of where they were discovered. We have things like Californium, sometimes they're named after famous scientists and people like Einsteinium, Nobelium, so, there's a lot of sort of sources of where names for symbols come from, and also why sometimes we do get what might appear to be kind of estranged symbols for elements. So as I alluded to before, when we do write symbols for elements, like you find on the periodic table, there are either one or two letter abbreviations. And definitely for sure, if it is one letter, it is always capitalized. And if it is two letters, the first letter is capitalized, the second one is not. So a good example of why you want to make sure you don't sort of capitalize everything is sort of like the example that they put there. If we use capital C lowercase o, that is the element cobalt. If you wrote capital C capital O and you meant cobalt, you're actually not saying cobalt. You're actually saying carbon monoxide, which obviously these two things are very, very different. And this also represents that we have an oxygen atom and also a carbon atom here, where this guy represents all we have is obviously the cobalt atom. So very important. Again, sometimes people do write there are some people that write everything sort of all capitals, letters and stuff like that. And you definitely don't want to do that, especially when you're dealing with chemical symbols, because you might actually be, kind of saying something you really are not intending to say by doing all those capitalization. So this is a table, and obviously your book or, or a periodic table you might have in front of you. These are the names and the symbols. It looks like they're in alphabetical order. And again, you can see some are two letters, some are one letters, things like aluminum here. We have carbon, calcium, cadmium, bromine, boron, barium. Again, some that, sometimes people are unfamiliar with. We have lead and iron here. Said it backwards there. Lead being the Pb, the iron being the Fe. We also have gold, which is Au. That is something we see come across a lot. Chromium, cobalt, chlorine. And again, this is why some of these abbreviations are what they are, kind of from the origin of these names. Again, why gold is Au here rather than, GO or something like that. Also why, again, iron is Fe, and also lead based on like a plumber type name, as Y as PV. Some other ones, this is mercury. That's one that, we do come across a lot. So that actually is HG. Tin is another one here. Again, one where you might think T would be involved with a name like tin. But again, the symbol there is SN. Silver, we see a lot. Also, again, based on the origin, a lot of why the name is like that. Potassium, again, that's one, right? It's based off of that. So these are the names, the symbols. I'll be honest with you, you should be pretty familiar with the names and the symbols. If you don't have sort of that understanding of the names and the symbols, you do want to take some time probably now to start getting that familiarity with it. We definitely will in the next chapter, I think, start talking about naming and how to name everything and all the rules that go with that. So, if you're still sort of struggling with, what is the symbol for nitrogen, or what is the symbol for platinum or neon or things like that, you don't want to have that in addition to trying to figure out how to properly name everything along the way. So it's really good to have some of that name and symbol recognition. So in general, if you sort of look at on a periodic table, there's a lot of ones that commonly come across. So if you kind of look on this side of the periodic table, a lot of those elements on the first two kind of groups, we do come across a lot. Usually, this part of the periodic table, a lot of those names, we do run into the first couple rows there, along with some of our guys, in this region as well. So, these are some common names and places on the periodic table that we do see a lot of it. We don't do too much of those two rows on the bottom all that much, except for maybe uranium, but not too many elements in there. Not a ton of elements, usually on kind of the bottom part here. We don't really do too much of those sort of symbols and stuff like that. So, a lot of the ones that we see on these tables are common ones that we do come across. So you might want to make sure, you get some of that familiarity with that, so you understand sort of what's happening. And again, although chemical symbols uses the letters of a lot of the current names, some of them are derived from sort of a long time ago and sort of names that was commonly used for them, again, like silver and gold, which again are two common ones that are kind of mixed up a lot. Again, silver is AG and gold is AU, and again, based on sort of those more historical type names. So if we want to write the correct symbols for each of the following here, iodine is I, just to kind of go through some of these. Iron, as we talked about, is Fe, again, capital F, lowercase e. Magnesium is Mg. Zinc is Zn, and lithium is Li. So again, these are the correct way to write the symbols for those guys. And again, here, if we were given the symbols, P is phosphorus. And again, the more you sort of get an understanding of the symbols and their names, much easier sort of the nomenclature and the naming stuff we're going to talk about in the next chapter is going to be. So AR is argon. Mn, again, is not manganese. I'm sorry, it's not magnesium like we just talked about, but it is manganese. Be is beryllium. And K, again, is potassium. Some other ones like sodium, for example, that's again another one that sometimes people, think it's kind of weird because it's Na is the symbol for something like sodium. So again, if you're not 100% on a lot of these sort of symbols, you do want to kind of take some time and learn them. Do you need to learn every single 109 symbols that are on the periodic table? The answer really is no. If you look at that periodic table, like I said before, kind of to the left of the periodic table, kind of to the right and up on the periodic table, and kind of right dead in the middle, the first couple of rows. Usually if you look at a periodic table, you see sort of this sort of situation in the middle. So, the first few rows, couple of rows here are common sort of symbols that we do talk about, when you kind of look at a periodic table. A very bad drawing here of a periodic table, but kind of like that. So, in this area and down in this way, it's a lot of what we deal with. And like I said, a lot on the outside, and a lot of the periodic tables, you'll kind of see a staircase coming down. A lot of the guys on top of that staircase and kind of below that staircase, these are very common places and symbols and elements that we do come across a lot in chemistry. And again, like I said, not too much going on, especially in our class, on those bottom two rows that are usually found on a periodic table, except for maybe, like I said, uranium. And, in this section of the periodic table, depending on when your periodic table is made, it may be very big, maybe kind of smaller, but not so much happening, sort of in that area either, of the periodic table. All right, so now we start to talk about elements, and again, the proper way to do their symbols. We're going to talk a little bit about the atom and just a couple of events that led to really our understanding of the structure of the atom and sort of what led up to it. So the atom, again, is really the smallest part that represents an element. And even though atoms are super extremely small, it was found that they had even a smaller particles that are present, and those are sometimes referred to as subatomic particles. So again, even though atoms are really, 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 really small, they do contain these subatomic particles. And three such subatomic particles is really the structure of an atom. Those are things that are protons, and as we'll talk about, protons are positively charged guys. They are electrons, which are negatively charged, and we have neutrons, which have no charge. So a lot of what we're going to talk about really helped us and understand the atom, and sort of led to more understanding about these three different sort of particles. So the idea of atoms did not really become a scientific theory until about 1808. A guy by the name of Dalton developed an atomic theory that atoms were responsible for really the combination of basically the compounds that we see. So Dalton's big idea, or one of his big ideas, was really when elements come together in forms of atoms, they do come together in these sort of ratios, and they do lead to really a combination of different compounds being formed as a result of what atoms came together from what elements, how many of each one. And he did come up with sort of a atomic theory, and these are some of the important parts of Dalton's atomic theory, which again you should be familiar with. And because it's a theory, a little bit of what we talked about in sort of the first chapter, that again, a difference between sort of a theory and a law is a theory may turn out to be maybe not correct in all cases. And that's sort of the case here with Dalton's atomic theory. There's some of the parts of it that are not necessarily correct in all aspects of it. So what he said was that basically all matter is composed of these tiny particles called atoms. He said that all atoms of a given element are identical to one another and different from atoms of different elements. Atoms of two or more different elements combine to form compounds. And when we do get a particular compound, it is always made up of the same kind of atoms and the same number of each kind of atom. So it's really kind of the same ratio based on how, say, for example, like in water, we get 2 hydrogens for every oxygen. It always comes together sort of in that proportion when we're dealing with water, or basically, hydrogen and oxygen comes together in that sort of manner, kind of every 2 grams of hydrogen for every 8 grams of oxygen. And he said that basically in a chemical reaction, basically involves a rearrangement, separation, and combination of atoms. We don't create nor destroy atoms in a chemical reaction. So a couple of things that were found not to be 100% correct, even though again, these are the main points of his atomic theory. One thing was he also thought that atoms were basically indestructible. And atoms actually can be sort of destroyed in that sense in like nuclear reactions, which we don't really talk too much about in this class. But in basic chemical reactions, it doesn't really happen. But in something like a nuclear reaction, you actually can change an element from one element to the next. That's very common of what happens. The other thing that's not 100% correct is the second one here, that all atoms of a given element are identical. And in this chapter, we will talk about something known as isotopes. And isotopes are the same element, but different masses, which means that even though they're the same element, they do have different masses, which means that those atoms are definitely not going to be identical to one another. So again, not correct in all aspects of Dalton's atomic theory, but again, these were the four sort of major points in terms of Dalton's atomic theory. So with sort of Dalton's atomic theory and a lot of sort of experimentation that came about, as I mentioned before, even though atoms are these really small sort of particles, it was obviously believed that they were composed of even smaller particles. And as I mentioned earlier, those are the subatomic particles. Again, our protons being positively charged, our neutrons having no charge, and our electrons having a negative charge. One important sort of relationship when we talk about things with charges is the idea that, much like in life, opposites attract, right? So, if you get two positive people together, they really don't want to be around each other. Get two negative people, they don't probably want to be around each other either. But if you get a positive, negative person, maybe they do balance each other out. And the same thing happens with things with charges. Things that have the same charge repel each other. So if you get two positive guys near each other, they definitely don't want to be there. If you get two negative guys near each other, they really don't want to be there. But when we do get a positive and a negative guy near each other, they are definitely attracted to each other. It's the basis, as we'll talk about, of ionic bonding. It's the basis of a lot of what happens. And the sort of idea of these charged sort of particles and stuff like that really was very instrumental in a lot of experiments that were done early on to help us sort of understand perhaps what the atom might look like. And really the kind of big major understanding of one of those type of particles, which are electrons, was done by a guy named Thomson. Thomson did experiments with a cathode ray tube. They're sometimes referred to as the CRT tube. And you might be familiar with cathode ray tube if you've seen maybe an older sort of TV that has like not a flat screen, but has like a real back to the TV that you could take off, and there's all kinds of stuff in there. You'd have picture tubes in there, and that was a CRT tube. Old computer monitors as well. Again, no flat screens or anything like that, but those old computer monitors that also kind of came out, with the big back in it, also were CRT monitors and cathode ray tubes. And what is a cathode ray tube? Well, honestly, a cathode ray tube is really just a kind of a beam of electrons, basically, was found to be these negatively charged electrons within an electrical field. So they had a negative side and a positive side in an electrical field here. And as we just talked about, these electrons, which are negatively charged, would be heading towards the positive side, away from the negative side. And on these tubes, they sometimes will put some type of fluorescent material at the end of it. So as the beams will come this way, the particles would hit it. You could actually see it kind of light up. And Thomson did a lot of work with the CRT tube, gone with a guy named Milligan, who did an important experiment, which is referred to as the oil drop experiment. And what Milligan was able to do, he also used sort of like an electrical field. And oil drop experiment is just that. He basically threw oil droplets into this sort of container. And what the oil droplet wanted to do by natural sort of process is fall, but it would gain a charge as it started to fall in this sort of chamber. And he was able to basically adjust the electrical field in such a way that the actual oil droplet would actually just be kind of suspended there. It wouldn't fall, wouldn't go up. And really, the combination of these two guys here, these two guys really helped us understand the electron and the nature of the electron. Thomson was really able to figure out the charge to mass of an electron. He was able to figure out the charge to mass of an electron. And Milligan was able to figure out the charge of an electron. And what each of these guys sort of experiments put together was able to do was able to for us to sort of understand the mass of an electron. They were able to also determine the electron is negatively charged and the mass of an electron in terms of its value. And that mass of an electron, is something like 9.09 times 10 to the minus 20, 28 grams. So the mass of an electron was very, very kind of small. So it's something like 9.09, give or take, times 10 to the minus 28 grams. So it's a very, very sort of small number there. And they were able to come up with that idea. So after those experiments, they sort of proposed an idea of what they thought the atom really kind of looked like. And really an early model of what they envisioned the atom looking like was one that's referred to sometimes as the plum pudding model. So Thomson came up with this idea of a plum pudding model. And the idea was they felt that all the positive charge was pretty much smeared and spread out over the sphere, where we had all these negatively charged electrons sort of embedded inside. So plum pudding is like a little rice dessert there, where you got like a rice pudding with a bunch of raisins sort of in the pudding. And that's sort of what he thought and then visualized that the atom was like that. And he thought that also that most of the mass of the atom was the electrons. So that was a very sort of early understanding of the atom, as we'll talk about. Not going to hold up this model of the atom, but again, that was sort of this really early rendition of sort of what we thought the atom was, that we had all this positive charge spread out because they felt that the atom was definitely electrically neutral. So they were able to discover these negatively charged electrons. So they felt that there had to be some positive charge somewhere. And again, that would be spread out. And this was all good for a while until really the kind of big experiment was done here. And the big experiment was done by a guy named Rutherford. He did what is referred to as the gold foil experiment. And the gold foil experiment was one where he shot alpha particles at pieces of gold foil and other metals. Alpha particles are positively charged radioactive particles. They were later found to really be like the helium nucleus, or kind of a helium atom, if you will. So what he did was he anticipated that he was going to shoot these alpha particles at this atom, basically. And the alpha particles positively charged, all that positive charge is spread out. So we have positive at positive interacting, which means they're not going to really want to be near each other. But these alpha particles are heavy, they're moving really fast. So what they expected to happen was they expected it to go through with some deflection. So kind of like if you took a piece of paper and you spread it out and, you held both sides really, really tight and you shot like a pencil at it, right? It probably would hit it and have a little deflection as it went through, but it would probably be able to go through. But it would hit a little bit of that deflection as it sort of went through. So they set up this experiment to basically see if that was the case. So they have this sort of source of alpha particles, as you can see here. They shot at these pieces of gold foil, and they were kind of surprised at sort of, what they saw occur. And what did they see occur? Well, they saw occur that for the most part, they had this little detector here so they could actually see where the particles are hitting. They saw for the most part that most of the particles went through undetected. So undeflected, most of them just had no problem, sailed right through, not a problem at all. But they did see that every so often, they would find an alpha particle being deflected at these really big, large angles. They even saw some maybe come back towards the source of it, and they were going and being deflected at really, really large angles. So they saw some being deflected at large angles. So what does that mean if something was able to deflect it at really large angles? Well, since we're shooting these alpha particles, which are positively charged, the only way it would reflect off at these really large angles is it had to hit something that was very densely positively charged. And this was not really what they expected, because if you remember, they expected that, like in the plum pudding model, all the positive charge is spread out all over the atom, right? It's everywhere. And they didn't expect what they found, because they found a lot of those particles had no problem, went right through, which means because those particles went right through, it pretty much hit nothing, right? It didn't hit anything. So what that means is it probably went through empty space. So this was actually very surprising to Rutherford based on sort of the accepted version of the model at that time, which was the plum pudding model. So what he said was, essentially, we have to look at that early model of the plum pudding model and go, not so correct, and how to sort of redefine what we think the atom looks like. And basically what he said was, definitely what's accounting for those alpha particles that are scattering at these really large angles is it had to hit something very, very positively charged, very densely positively charged. And he called that basically the nucleus. So the nucleus basically is in the center of the atom. It is very positively charged, which we'll talk about later, found to contain protons, which is why it's positively charged. Later as well, found to also contain neutrons in 1930s, which have no charge, and these guys are found. Also said that, most of the atom is probably empty space. Which again accounts for why most of those particles sail through with no problem. And electrons are out from the nucleus at some distance, and they are traveling randomly, as we'll talk about. Again, they're not traveling in pretty patterns. They're traveling pretty randomly about the nucleus. The other major sort of difference between sort of the really current model of the atom that came out of Rutherford's experiment is that most of the mass of the atom is the nucleus. So the nucleus makes up most of the mass of the atom. And the reason for that is because the nucleus contains both protons and neutrons. And in terms of protons and neutrons, a proton or a neutron is about 1,800 times heavier than any electron that's flying around. So the mass of a proton is significantly greater than an electron, and the mass of a neutron is significantly greater than an electron as well. And that's why I also had to kind of throw out the idea here in the plum pudding model that the electron was most of the mass of the atom, and that the nucleus is actually the place where we contain most of that. Just so you know, and as we'll see, I think the neutron is actually the heaviest of all three of those, followed very, very closely by the proton. They're almost identical to each other, but there's a slight difference, and the neutron is the heaviest. And the electron, like I said, is about 1,800 times less heavy than a neutron or a proton individually, and it is actually the lightest of those three sort of subatomic particles. Any questions on that there? So again, based on sort of the experiment here, an atom consists of a nucleus, which contains protons, which are positively charged. In about 1931, a guy named Chadwick basically discovered neutrons that had no charge. And again, both of those guys are found in the nucleus. They are both way heavier than any electron that's outside sort of flying around. And again, most of the atom is that empty space. Any questions on that there? Now, when we talk about the mass of an atom, we oftentimes talk about it in the sense of a atomic mass unit. And atomic mass unit is the mass of an atom that's due to its protons and neutrons in the nucleus. Electrons, as I talked about earlier, has a very, very small mass in comparison to a proton or a neutron. Atomic mass unit is equal to 1/12 the mass of a carbon-12 atom. So when we talk about atomic mass, and you look on the periodic table, since we talked a little bit about the periodic table there. The number that we see on the bottom on the periodic table underneath the symbol, that actually is the atomic mass of an element. And it is given in AMU, which is atomic mass unit. And you may wonder, like, and which we'll talk about in this chapter, how, we get these numbers. So the carbon-12 isotope was really the standard by which they chose. And they did that because they said that carbon-12 had a mass of exactly 12 AMU. So as we'll talk about, essentially how we get these atomic numbers here on the bottom is they did some experiments and said, well, hydrogen's only like 8% as big as a carbon-12 isotope. So they basically take 8% of 12 and they come up with that 1.008 number that we associate with hydrogen in terms of its atomic mass. The atomic mass of a proton here in AMU is 1.007. You can see, as I was just talking about, the neutron is super close to it, just about a hair difference there. And you can see a very significant difference in the mass of an electron, much, much smaller in terms of its value. And again, we did the electron to the minus 28. The mass of a neutron or proton is like 1.6 times 10 to the minus 24 grams. So it's much, much heavier than an electron. Here again is sort of the relationship and some of the symbols that we commonly see. A proton is symbolized sometimes with a P or the P with the plus. Again, it has a positive 1 charge, and our neutron has no charge, and our electron there has a minus 1 charge, again, flying about the nucleus. So you do need to know, obviously, where we find protons and neutrons in the nucleus. Electrons are flying around the nucleus. Is there attractive forces between the nucleus, which is positively charged, and those negatively charged electrons? There is. And as we'll talk about in a later chapter in terms of bonding, that's why certain electrons are involved in bonding, other ones are not, because of that attractive force. But again, a reminder, we'll talk about more, electrons do not travel in pretty circles or anything like that. They actually don't. They travel very, very randomly about that nucleus within that empty space that Rutherford found in his experiment. Any questions on that so far? So let's take a look at some of these questions here. Which of the following subatomic particles fits the descriptions? Found outside of the nucleus. Again, that's going to be our electrons that are flying around. Has a positive charge. That's going to be our protons found inside the nucleus, and has a mass but no charge. That's going to be our neutrons, also found in the nucleus of an atom. Any questions on that particular one? And each of the following, which one is true or false here? So the mass of an electron is greater than the mass of a proton, and that is definitely going to be false here. Again, the electron is the lightest of all three of those particles, with the neutron again being the heaviest, and the proton pretty darn close to the neutron, but still slightly less than a neutron. Protons have a positive charge and electrons have a negative charge. That is true. Again, in the nucleus, out of the nucleus in terms of that. The nucleus of the atom contains only protons and neutrons. That is also true as well. So again, here's sort of a picture of the modern day and acceptable sort of version of the atom. And a little hard maybe to pick up here, but again, this is our nucleus. Very, very small compared to the size of the atom. You can think of the atom as like a big stadium, and like the nucleus is like a marble there on the 50-yard line, for example. It does have our protons and neutrons inside. And in this sort of empty space, you could kind of maybe get a hint of the blue color that's happening here. That's that empty space. That's sometimes referred to as the electron cloud. That's where our electrons, again, are moving about in this random sort of motion. And that electron cloud is really sort of what was described in Rutherford as sort of that empty space. So you definitely need to know the structure, obviously, of the atom, where all those particles are located, the charges of the particles. You need to know, obviously, the differences in the mass. You don't need to know the exact numbers, but you do need to know, obviously, that the neutron is the heaviest, the electron is the lightest. And you need to know a little bit about Thomson and Rutherford and Milligan, just, kind of, what those experiments sort of led to. No great detail. Obviously, we didn't go into giant detail on those things, but, you kind of have some understanding of those things. Any questions on any of that? Okay. So now let's talk about some properties associated with atoms, and we're going to talk about atomic number, mass number, and isotopes. So we'll start with the idea of, as sort of Dalton sort of explained, a lot of what happens with atoms, a lot of the chemistry and normal chemical reactions really involve electrons. So electrons, if you think about the atom itself, we have our nucleus, we have our electrons on the outside. So, when two atoms sort of come together, they're kind of the first ones to say hello to each other. So it is the basis of like all types of bonding that we'll talk about in this class. Ionic bonding, covalent bonding is that interaction of electrons. When we do chemical reactions, essentially, everybody breaks apart, which is breaking apart electrons and bonds and stuff like that, and sort of reassembles. The first sort of important part of an atom in that sense is what is known as the atomic number. And the atomic number is sometimes abbreviated with a Z. The definition of the atomic number is the number of protons in the nucleus of an atom. The atomic number can actually be found right there on the periodic table. Looking at the symbol, it is the number up on top of the symbol. So that number that you see up on top is the atomic number. So for hydrogen, that is 1. If you look at oxygen, that is 8. Chlorine, that is 17. So all the numbers that you see up on top tells you the number of protons, which is the atomic number. If the atom is neutral, and if you think about the atom, it is basically made up of 3 things: protons, which are positively charged, electrons, which are negatively charged, and neutrons, which have no charge. So in terms of if it is electrically neutral, and you know the atomic number, which is the number of protons, to balance it out, that would also be the number of electrons an atom would have. So if you're dealing with something that has no charge overall and is neutral, the atomic number will also tell you the number of electrons that there are. An important distinction, though, in that is if you are asked straight out the definition of, like, what is the definition of atomic number, the definition is only the number of protons. It is not the number of protons and electrons. If you're asked that specific question of what does the atomic number actually mean, the actual definition is just the number of protons. Second to that is if it is neutral, it will also tell you the number of electrons. But as we'll talk about, if it's not neutral, it will not tell you that number correctly. So the only definition really is atomic number. If you also look at the periodic table on all of those numbers that come on top of the elements, you will see that no number repeats. And what that means is every element has its own atomic number, which means a couple of things. First off, it means that it is the protons that determines the element we're talking about. So if you know the atomic number, which means by default you know the number of protons, that also means that you know what element you're talking about. You could simply go to the periodic table, take a peek, find the top number, and you'll know the number of protons and what element you're dealing with. So for example, if we go to the periodic table and look at our good friend nitrogen, we will see the number 7 up there on top. That means, as it says there, that nitrogen that is neutral should have 7 protons, which are positively charged. Also should have 7 electrons, which are negatively charged. That means overall no charge, and we know that for sure. If I say, hey, I have a nitrogen atom that has 15 protons, you should tell me you don't have a nitrogen atom that has 15 protons, because if you look at the periodic table, number 15 is phosphorus. So because it's 15 protons, it has to be phosphorus. And if we had a neutral phosphorus atom, we would also have 15 electrons as well. Any questions on that? Atomic number, number of protons found in the atom. That number can be found on the periodic table above the symbol. And because every element has its own atomic number, you could actually identify the element simply by knowing the atomic number or the number of protons, which is essentially the same thing. Another important aspect of this is what is referred to as mass number. Mass number is sometimes abbreviated with an A, and it is the number of protons plus the number of neutrons that are found in the atom. So the mass number is the number of protons and the number of neutrons. Now, the atomic number that we just talked about is the number of protons. And the nice thing about both of those numbers is if you take the mass number, which is our number of protons plus the number of neutrons, and you subtract it from the atomic number, which is the number of protons, those will cancel, and you can find the number of neutrons by doing so. So by taking the mass number minus the atomic number, that will allow you to find the number of neutrons that are present in an atom of an element. Any questions on that there? Now, when we sort of calculate those things or find those things, the number of protons, the number of protons, the number of neutrons, the number of electrons, the atomic number, the mass number, all those things, as we see down here, they all should be positive whole numbers. So if you're asked to calculate, how many electrons there are, if you ask how many protons or neutrons there are, or what the atomic number or mass number is, it all should be positive whole numbers. You can't have like a half an electron or anything like that. You know, you got to have a whole one and stuff like that. So that begs the question that when I go to the periodic table and I see my hydrogen with a 1 and a 1.008, or maybe I go and I see my oxygen with an 8 or a 16 on the bottom, you know, is this bottom number here the mass number? And the answer is no, it is not the mass number. So very commonly made a mistake by a lot of people is they will go to the periodic table and go, oh, the atomic number is on top. So clearly that bottom number is the mass number. And as I spoke about just a moment ago, the bottom number is not the mass number. It is actually the atomic mass, which we'll talk about in this chapter. And it is slightly different. What confuses people sometimes is when you calculate the mass number or something like that, it will actually be a number very close to the atomic mass. But the one way you could really remember that the number that you see on the periodic table there is not the mass number is by the last thing that's written there, that the mass number, the atomic number, the number of protons, electrons, and neutrons, they all have to really be whole numbers. And if you look at most of the values that you see on the bottom on the periodic table, they're for the most part not whole numbers. So there's a lot of decimal numbers and stuff like that. So again, that's a good way you could kind of remember that, oh, those things are not the mass number because they're definitely not whole numbers. Any questions on that? So only the atomic number can be found on the periodic table in this context. And again, that's the number on top, which is the number of protons. You'll be given enough information to figure out protons, electrons, and neutrons, but definitely that number below the symbol is the atomic number and definitely not the mass number. Any questions on any of that there? So as I mentioned earlier, the idea when we talk about Dalton's atomic theory that, you know, there are the existence of isotopes, and what isotopes are the same element, but they basically have a different mass. So as we just talked about, in terms of protons, electrons, and neutrons, the one particle that's really important in terms of determining what element we're dealing with is the protons, or the atomic number. So when we're dealing with isotopes, what we're dealing with is basically the same element because they all contain the same number of protons. And what that means is typically the difference between them is the number of neutrons. So usually in an isotope, that is usually an element that has obviously the same number of protons. Otherwise, they wouldn't be the same element, but different numbers of neutrons, and that is why they have a different mass. So one way that we very commonly represent isotopes is to write the symbol like we see on the bottom here. X represents this symbol. Top left, we put the mass number. Bottom left, we put the atomic number. So if we look at hydrogen, for example, hydrogen, deuterium, which is heavy hydrogen, tritium, which is the radioactive version of hydrogen, we could actually write the symbol for each of these isotopes. So if we start with hydrogen, we know it has one proton. One proton means the atomic number is 1. So if you were not sure, you could go to the periodic table and you would see number 1 is hydrogen, H. One proton means the atomic number is 1, which would go bottom left. Top number would be the mass number. So again, the mass number is our number of protons plus our number of neutrons, which in this case is 1 proton plus no neutrons, which means the symbol for hydrogen would look something like this, 1 up on top. If you subtract the top number from the bottom number, 1 minus 1 gives you 0. That is the number of neutrons. Now, every single element has protons, electrons, and neutrons. The one exception in terms of elements is hydrogen, as we see here. Hydrogen has a proton, hydrogen has an electron, but hydrogen has no neutrons. It is the only element that doesn't have neutrons. Everybody else will have some type of neutrons. When we go to deuterium here, even though it's called deuterium, has no indication by that name that we're talking about hydrogen. We know we are talking about hydrogen because we see it has one proton. And because it has one proton, if you went again to the periodic table and found number 1, you would find again the hydrogen symbol there. And again, it would have an atomic number of 1. But in the case of deuterium, it also has a neutron, which means the mass number for that guy would be 1 proton plus 1 neutron would give us 2 for the mass number. Again, if you take the top number minus the bottom number, 2 minus 1 gives us 1 neutron. So that would be the symbol for deuterium. Again, even though the name, you might not imply to you that you're talking about hydrogen, because it only has 1 proton, it really is still hydrogen. Same idea here when we get to tritium. Again, you might not even recognize that as really still being hydrogen, but when we look at it and we see 1 proton, that automatically tells us the atomic number is 1. Just like the other 2, when we would go to the periodic table, we would have 1. But this guy has actually 2 neutrons, which means its mass number would be 1 proton plus 2 neutrons, which would be 3, and it would be 3. So these are 3 representations of isotopes. They're isotopes because ultimately, even though they got different names, they all contain 1 proton and has an atomic number of 1, which ultimately means that they are all hydrogen, no matter what their name is called. But the difference is, and why they are isotopes, is they do have different masses because they essentially have different mass numbers, which ultimately means they have different numbers of neutrons in each case. Again, the first one having no neutrons, second one having 1 neutron, and the third one having 2 neutrons. So that's a very common way to represent isotopes. Another common way to represent isotopes is something like this, Cu-64, for example. That is copper 64. You may wonder, what does that number represent? Well, if I go to the periodic table and I look at copper, and if I look at copper, I will see up there on top of copper is the number 29, which means that is the atomic number for copper, which by default would mean that this number is not the atomic number. This number is actually the mass number. So that's, again, another common way sometimes isotopes are written. The elemental symbol dash a number. That number usually represents the mass number in that particular case. Any questions on how to write the symbols, figure out protons, electrons, and neutrons? Okay, so why don't you take a second here and see what you come up with for this one. We got 3 different elements. We're looking for the numbers of protons, electrons, and neutrons in each of them. So take a minute or so and we'll talk about it. Okay, so let's see. I see some numbers rolling through here. So let's take a look. So again, we're looking for the numbers of electrons, protons, and neutrons in each of them. And again, we're written with our symbols here. So a reminder that when we look at the top number, that is the mass number. And again, that is our number of protons plus our number of neutrons. When we look at the bottom number, that is our atomic number, which is our number of protons. And also really important here is the idea, does this thing have a charge? So in case you're not sure, if something did have a charge, we would see it right about there. And clearly we see nothing written there, which means it doesn't have a charge. So that should mean that it is neutral in this case. So for our first one, which is cobalt CO, the number of protons in this case, the number of protons will equal the atomic number, which is 27. Again, that's 27 positive guys. And because it is neutral, it also should then have 27 negative guys, right? So if you take 27 positive guys and you add them to 27 negative guys, you end up obviously with no charge, which is what we see here. Now, in terms of our number of neutrons, we take our mass number minus our atomic number. So our mass number in this case is 60 minus our atomic number, which is 27. And that looks like we end up with 33 in terms of our number of neutrons. Any questions on that one there? Looking the same approach here, again, bottom number going to be our number of protons, which is our atomic number. Also, again, we see no charge there. So the number of protons in this case would equal 17. Again, that's 17 positives. And because it is neutral, we should also have an equal number of electrons, which are negatively charged. Our number of neutrons, again, taking our mass number, which is 37, minus our atomic number, which is 17, going to give us 20 in that particular case. Any questions on that one? Looking good there in the chat box there, looking like we're getting the right answers, so that's good. So let's take a look here at the last one, U, which is uranium. Again, we see no charge associated, so we know it's neutral. Again, looking at the bottom number, which is the number we could find on the periodic table, and also our atomic number would tell us, in this case, we got 92 protons. Again, because it is neutral, we would also have 92 electrons. And our number of neutrons, our mass number, which is 238, minus our atomic number, which is 92. That gives you a big number, a lot of number there. Let's go with 146, I think, in terms of the number of neutrons. Any questions on how to calculate those guys there? Okay, so why don't you do the next example here? So we want to write some symbols, I think, in this particular case. Maybe, let's see. That's good, they agree. All right. So why don't you try the next one, which is, I believe, so you got krypton that has 48 neutrons. I think the next one is nitrogen with 6 neutrons. And again, you might want to find a periodic table. It'll be helpful here. And we want the iron atom with a mass number of 56. What is the number of protons, neutrons, and electrons? So we want the element written with both the mass number and atomic number. So make sure you write with those numbers like this format for each of those. And then for the last one, also, we want to know protons, electrons, and neutrons. So again, take a minute or so and see what you come up with. Okay, so let's take a look here. See some answers rolling in. They're looking good too. So let's just go through them. So krypton atom has 48 neutrons. So we would first want to go to the periodic table, find the symbol for krypton, and that is Kr. Again, if you kind of went to the periodic table, it will look something like this with like a 36 there up on top. And again, it's that top number, right, which is the atomic number. So that will tell us that the 36 there should go on the bottom. So remember, atomic number there, bottom left. The other importance of that atomic number is that is the number of protons, right, would also be 36. That's important because they gave us the number of neutrons. So if we take the number of neutrons, which is 48, and we basically add them together, That's going to give us 84 for our mass number, right? Which the definition is number of protons and neutrons. 84 there would go up on top. Any questions on that one there? Okay, doing our next one, which is nitrogen. Again, if you go to periodic table, you should see N. And again, when you look at it on the periodic table, right above it, there is number 7. And again, that tells us that nitrogen has 7 for its atomic number. Again, the other importance of that is it also tells us that it does have 7 protons, along with the 6 neutrons that was given in the problem. Tells us in this particular case, we are looking for a 13 in terms of the mass number here by adding those together. And that is what should go up there, up on top. Lastly, iron. So again, iron is Fe. And again, if you went to that periodic table and found the box there with Fe on it, it would have a 26 up there on top, 26 being the atomic number. And that's what would go on the bottom left. In this case, they actually gave us the mass number, which was 56, which would go up on top. And in terms of what it got going on, because it has an atomic number of 26, that means the number of protons would be 26, along with our number of electrons, which would be 26. And our number of neutrons would be 56 minus 26, which would end up with 30, I believe, as our number of neutrons. Questions on how to write symbols, protons, electrons, neutrons. Now, you may have a question like all these guys were positive or not positive, they were all neutral. They had no charge. You know, what happens if we do hit something that has a charge? So while we're talking about this, let's talk about sort of what would happen if something did have a charge. So for example, if we do have something with a charge, those are what are referred to as ions. And these are things that do have charges. And there's really 2 types. There's a cation, which is positively charged, and there's an anion, which are negatively charged. So let's just take our good friend nitrogen here. And if we did nitrogen with the exact same numbers, the 13, the 7, but in this case, we decided to give it a -3 charge, which is typically what nitrogen would make. What does that really affect? So let's start with the number of protons here. So the number of protons is still going to be 7 because it is still nitrogen. It still has the same atomic number. In this particular case, the number of neutrons would be 13, which is the mass number, -7, which would give us 6. So that stays the same. So that means that really the only thing that's going to change is the number of electrons. So the number of electrons in this case is actually going to be 10 electrons. If you take 10 negatives and you add it to 7 positives, you are left with a -3 left over because you got 3 extra electrons. Yes. So what is the difference between nitrogen that had no charge and nitrogen with a charge? The difference is the number of electrons. The negative means that it gained electrons. The 3 is how many electrons it gained from the neutral element. Neutral element had 7 electrons. Guy with a -3 charge had 10 electrons, 3 electrons more. So usually when we get something that has a negative charge, the only thing that changes is it actually just gained electrons. And that's really why it's negative, because sitting in the nucleus is 7 protons, but sitting outside floating around is 10 electrons. So again, the overall difference here is we got 3 more electrons, which is where that -3 charge basically comes from. Question on that one. Now, let's say I took iron, for example, that has a positive charge. Yeah, so it would have 10 electrons with the -3 charge. Yeah, so when it gains that -3 charge, it actually has 10 total electrons. You know, if you just kind of want to do the math part of it, you could actually just even draw it out, right? You got like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. You have 1, 2, 3, 4, 5, 6, 7 protons. These two cancel, these two cancel, these two cancel, those two cancel each other out, they cancel each other out, they cancel each other out. And as you can see, we are left with 3 extra electrons, and that is where the -3 charge basically comes from. Other questions on that? So let's say we take our iron, and again, do the exact same thing, 56 and 26. And we got a +2 charge on this guy. So our neutral iron has 26 electrons. This iron over here would also have 26 protons, right? Because the atomic number is still 26. Just like over here, it would still have 56 minus 26 for the number of neutrons. So again, here, the difference is going to be the number of electrons. This guy would actually have 24 electrons. 26 positive guys plus 24 negatives leaves us a +2 left over. And that is where the +2 charge comes from. The difference between the neutral guy that has 26 electrons and our guy with a +2 charge is the plus means that it lost electrons. The 2 means it lost 2 electrons from its neutral guy. And that is what happens when we have something that becomes positively charged. It typically has lost electrons. So when something gains a charge, really the only thing that changes is the number of electrons. It cannot be the number of protons, because if we change the protons, we do change what element we're talking about. Any questions on that there? So, and again, the idea here is, in this case, you got like a +26 with all those protons, but floating on the outside, there's only 24 negative guys. So again, the difference between those two is going to be that +2 difference overall. All right, so why don't you try just a couple here? We'll wrap up on that probably. We got, why don't you do, let's go with aluminum with a +3 charge that has a number of 13 down there. And we'll do, let's do 27 up on top. Let's also do maybe, let's do chlorine here with a -1 charge, and we'll do 17 on the bottom, and we'll do 36 up on top. So for each of these, how many protons, electrons, and neutrons are there in each of these guys? So take a minute and then we'll talk about it. Okay, so since we're getting to the end, let's take a look and see what we got going. So we'll start with the aluminum, has a +3 charge. First off, the easiest thing to figure out, obviously, is the number of protons. That is going to be our atomic number, which I scribbled really badly here. That is going to be number 13 positive guys there. Other thing for sure easy to figure out is our number of neutrons. So we're going to subtract the top number from the bottom number. I can go with 14 on that. So that leaves us our electrons. So what do we know? Well, we know that it is positively charged. So what that should automatically tell us is that it lost electrons. And what did it lose electrons from? It lost electrons from its neutral guy, which means in the neutral, it has the same number of electrons as protons, which means we actually would have 10 negative electrons in the case of the top one. Again, 13 positives and 10 negatives leaves us that +3 charge that we see here. really because we have 3 more protons than electrons in this case. Question on that first one there.
When we write for electrons, do we write it as -10?
If you're just asked a simple question of like how many electrons there are, you could just write 10. I'm just putting the positive and negatives so you can maybe visualize, we take 13 positives away from 10 negatives. But if it's just a straight question of, what's the number of protons, electrons, or neutrons, you could just write the number in that case.
Okay, thank you.
You're welcome. Other questions? Okay, so looking at the bottom one there, we got something there. We got chlorine. And again, the easy place to start probably is our protons, which would be 17 in this case. Again, taking our top number, which I wrote really badly there. I think that's a 36 I wrote. And our bottom number, which is our atomic number. So we would take 36 minus 17. And I believe that is 19 for our number of neutrons. Now, in this case, we do have a negative charge, a -1 basically. Negative means that it gained. The number is 1, which means it has 1 more electron than the neutral guy, which basically means the neutral guy has 17 electrons. This guy would have to have 18. Again, 18 negatives and 17 positives leaves you 1 extra electron, which is what accounts for that -1 charge. Question on how to assign electrons, protons, neutrons to things that are neutral, to things that have charges, how to write the symbols. Any questions on any of that stuff we talked about here today? Okay. So we will stop there today. Let's talk about, more importantly, the scheduling that's coming up. Find somewhere to write, maybe. Wherever I scribbled, I'll scribble here. So as of now, scheduled for next Wednesday, and that would have been, I'm not even sure what that would be. That was March, actually, right? So that's 1, 2, 3, March 3rd, I think. Was exam 1. I don't think that's going to happen. So not going to happen here because we're going to finish chapter 4, I think, before exam 1. So for the time being, I think realistically speaking, we're looking at first, second, third. So probably we'll go the following Wednesday. So I think that is probably, hopefully the 10th is probably where exam 1 will be. And again, it will cover chapters 1 through 4. So I'm pretty sure we'll probably hopefully get through chapter 4 on Monday. And like I said, we'll finish up that chapter 3 as well. Homework will be moved. I haven't had an opportunity yet to do so, but I'll do it in the next day or so. But the homework will be extended, obviously, until that day as well. Any questions on that then? Okay, so if you haven't done so already, make sure you do put here. If you're out for the weekend and have lab, have a very nice weekend. Those people, again, that are scheduled for discussion today, we will be lecturing a little bit on chapter 3 just to get everybody in the same spot on chapter 3. And again, for everybody, at some point in the next couple of days, I'll probably post up there the rest of chapter 3 and sort of a recorded lecture, which I think is maybe one section to talk about. Other than that, I'll see everybody in discussion about 7:10-ish, maybe 7:12 or 13.